In this lesson, you will learn the second method to analyze a circuit, which is called nodal analysis. The nodal analysis is the approach used by most circuit simulators. The main advantage of nodal analysis compared to mesh analysis is that it does not require a complex algorithm to obtain the loops of the circuit. The disadvantage is that it can lead to having larger systems of equations to solve. Nodal analysis starts by identifying and numbering each node of the circuit. In this diagram, we have marked all the nodes with red dots and each one has a number. By convention, the ground node is the node 0. The next step is to assign a current symbol, including a direction for each branch. In this diagram, we take advantage of the differences in the positive and negative pins of the components, and every current follows the polarization markers. All currents enter through the blue terminal and exit through the white. Once we have defined the currents, we can start writing the equations. We will proceed node by node, starting with node 3. The equations follow the Kirchhoff current law, which states that in a node, the sum of all the currents must be 0. In the case of node 3, we have the current IR2 entering the node, therefore we write it as positive, and the current IR4, which is exiting the node, and we write it as negative. For node 2, we have 3 currents. We have IR1 entering, we write it positive, IR2 is exiting, so it's negative, and IR3, which is negative as well. For node 1, we have a special case. Even if we have these currents entering and exiting, we already know the voltage of the node. Therefore, we don't need to write an equation. In this case, we know the voltage between these 2 points, and it's given by V1. So we only write the equation that V lowercase, which is the voltage of the node, it's equal to V uppercase 1, which is the voltage of the source. For node 0, we have a similar situation. By convention, the voltage in the node 0 is always 0, and we don't need to write an equation for it. We end up with the following equations for each node. The next step is to put the currents in terms of the voltages of the nodes. To do that, we use Ohm's law on each resistor. In the case of resistor 4, it is connected to nodes 3 and 0. Therefore, the current is the difference between those 2 nodes divided by the resistor value. Since we know that V0 is equals to 0, we can simplify the equation. Similarly, the current IR2 is the voltage difference between the nodes 2 and 3 divided by the resistor R2. Resistor 3 uses V0, and we can simplify the equation as follows. In the case of resistor 1, we replace the lowercase v1 with the known value v1 uppercase. That results in these 2 equations, which have 2 variables, v2 and v3. Using Wolfram language, we can easily solve these 2 equations. I have written the equations here, and using the command solve, we obtain these formulas, and we can replace the numeric values into those formulas in order to obtain the numeric results. Here is a list of all the steps that we need to follow in order to perform nodal analysis on a circuit. First, we need to identify all the nodes in the circuit. Then we need to assign a voltage symbol for each node. After that, we define the direction of the current for each branch. We write the equations of each node using Kirchhoff current law. After that, we rewrite all the current variables in terms of the voltage using Ohm's law. And last, we solve the system of equations. As circuits get larger, performing the steps to analyze a circuit can become more difficult and error-prone. That's where a simulator like System Modeler can help us to easily obtain results. With System Modeler, it's not only possible to obtain numeric results by running simulations. We can obtain equations of the circuits we simulate. However, System Modeler uses a slightly different approach. In mesh analysis, the equations are solved in order to obtain the currents for each loop. In nodal analysis, we solve for the voltages of the nodes. System Modeler solves for the voltages and currents on each terminal. This can lead to have more equations compared to the other methods. I'm going to show you an example of how this works. All the diagrams that you have seen in this course are made with System Modeler. This is the interface of System Modeler, and here we can connect the components, we can change the values, and of course we can run simulations. Once we have run a simulation, we can plot variables. So creating a diagram in System Modeler, it is quite easy. It's just dragging components and connecting them. Once we have created a circuit, we can use the connection with Wolfram language in order to get information about our model. Here I have assigned to the variable m my model, which is the one that we saw before, the one that we are analyzing with the resistors. And using this command, we can get the equations of the system. And as you can see, these are a lot of equations. We can see the names of the variables, like in this case, it is referring to resistor 2, negative pin, current, and we can see that variables like that for all the resistors. But there are lots of additional variables. For example, these are actual, heat port, etc., alpha. All these variables have to do with the models of the resistors. The resistors in System Modeler, additionally to the electrical part, they contain thermal behavior. So it is possible to calculate, for example, the losses, and also we can connect to the thermal world and perform also thermal simulations combined with the electrical simulations. So these equations are not very useful, and I'm going to show you a way of getting equations that are more compact and useful. To get simpler equations, we need to start with creating a simpler model of a resistor. System Modeler allows to create custom models if you need them or if they are not available in the library. Under the hood, there is this language called Modelica. Here we can see the code for a simpler resistor. You can see the most important part here is the equation, which specifies that the voltage is equal to the resistor times the current. This is the code that I use for this simpler resistor. After that, I have created the same circuit but using this simpler model. I have assigned the model to the variable nm, and now I'm going to get the equations, but I'm going to specify this elimination method, which will eliminate all simple and redundant equations. And here we can see that we have a smaller system of equations. The next step will be to solve this system. So we need to solve for all the variables that have the term t, which are the ones that vary in time. We pass to the solve command the equations and the variables that we want to solve for. And we obtain these long expressions, which are the results in a symbolic form. If these symbolic equations are too large for you, we can also do the same work but with the numeric values. And using this parameter values property, we can replace all the numeric values on the equations. By doing that, we obtain these which are the same equations but with the component values replaced. And we can solve the system as well using numeric computations instead. And here we can see the results. And as you may have noticed, we are solving for the current of the resistor 1, current of the resistor 3, resistor 4, etc. As a summary for this lesson, the nodal analysis is another alternative that we have to analyze complex circuits. This has the advantage that it's easier to automate. Nodal analysis defines one equation per each node of the circuit, and it solves for the voltage value of each node. System Modeler can help us to obtain symbolic equations in addition to simulate circuits.